Whenever someone hears the word physics, they either think about a bunch of formulas to memorize or relativity and quantum mechanics. But what is relativity? What is quantum mechanics? Hey guys, my name is a physics nerd, and today we're going to talk about special relativity and also time dilation. Whenever you might want to learn about a new physics concept like torque, motion, classical mechanics, whatever, you might just Google it and then look at the AI response and then just leave it there. But here's the thing. Sometimes the AI responses are wrong, which is normal, and they can be kind of confusing because they tend to just draw the information from other sources. And yes, it can be helpful for people that are just trying to get some quick information. But if you're trying to actually learn about the subject or about the topic, it's best to actually look at online videos or books. So what is special relativity about? Well, special relativity is just a more improved version of the laws of motion that we used to have, which basically says that in all inertial frames of reference or stationary frames, when you're not moving relative to everything else, the laws of motion are the same. And second, the speed of light is constant in a vacuum. And the speed is approximately 300,000 kilometers per second. Or for those who don't like the metric system, it's about 186,000 miles per second. And it's the fastest thing that anything can be. So that means the velocity has to be less than the speed of light. Because the speed of light, the light itself has no mass. So if this is a photon, let me use yellow. If this is a photon and it were going like that, we know that it has a mass. Let's say it had a mass 7. We know that equals 0 because it's just electromagnetic radiation. It's not a particle. It's just called a particle to show that light is something. It's not just energy. They're more specifically packets of energy. The particles are packets of energy. And it can be in a wave particle duality, but we'll talk more about that in another video. And because of that, if you had, let's say, a light cone or a light sphere that was expanding and you were in it, this light goes out more and more. So the light that's the most present is the one nearest to you, and the farthest one is the most past to your present. And the future light cone is the light that's about to be produced. But how do we show that time is experienced differently for all compared to inertial frames of reference? Well, we can use this example called a light clock. So we can draw 2 light clocks. One is just a stationary light clock. Well, where we can call the time it takes for light to go from one mirror to the other mirror as time stationary, or TS. But what if that clock was moving, which will be our second frame of reference, time for moving mirrors. So this is where we would expect the mirror to be. But we know that it isn't there. It moved a bit here. So the light is instead going to go like that. So this is going to be our moving frame of reference. And we know that light, for anything, the larger the distance it has to go, the more time it takes. So that means that time is dilated. That's all we need to prove it conceptually. But what if we wanted a mathematical derivation? Well, for those who don't want one, you can skip this part. Skip to the timestamp that's mentioned below. And so what we can do is we can say, well, the time it takes for light to go here, that's also time stationary. So that's also time stationary here. And this angle is called theta. And we know by our trig ratios that the sine of the angle theta is equal to the time stationary divided by the time for the moving mirrors. And we can rearrange this formula to solve for the dilated time, which is the time for the moving mirrors, and get that the time stationary divided by the sine of theta is equal to the dilated time. But how do we solve for sine theta? Well, we know that in this direction, the horizontal direction, the velocity is v. And we know that the time it takes for light to reach from one mirror to another mirror in a moving frame of reference is Tm, but we know the speed of light is constant, so that's going to be c. So so we can use our trig ratios, to say that cosine of theta equals v over c, where c is the hypotenuse, v is the adjacent. But how are we going to keep this in our formula to make sure that it's not in terms of trig ratios? Well, we can use our Pythagorean identity. Sine square of theta plus cosine square of theta equals 1. And rearrange it a bit to get that sine of theta equals the square root of 1 minus cosine square of theta. And we know that cosine of theta is v over c. So sine of theta is equal to the square root of 1 minus v over c squared. Now we can just plug that into our formula for the dilated time, and then we get this, that time dilated is equal to the stationary time divided by the square root of 1 minus v over c squared. And that's the mathematical derivation. Oh shoot. So now what would this mean? What would be different? Well, here's the thing. We know that usually whenever we want to get to a really far place, we would think we just need better technology to be able to go faster with our rockets. Let's say the Andromeda Galaxy. Yeah, I'm really bad at drawing. But we know it takes a lot of time, so we're going to try to go at the speed of light, c, or approximately c, because you can't go at the speed of light. And yes, this does work, but once you get back at about the same speed, many years would have passed by. Yes, for you it would have been really short amount of time, and because of length contraction and other phenomena that happen due to special relativity, but millions of years would have passed by on Earth. And who knows what would have happened to it. A mass extinction may have occurred, wiping out the human species. Maybe even the dinosaurs came back. Who knows? But it really depends on how far you're going and how close to the speed of light you're going. So yeah, that's another problem that comes from special relativity. Not a physics problem, or of a real life problem. Because what that means for space travel is, even if you had the technology to go that fast, that would not work as good, because yes, you're gonna get there, but many years are gonna pass by for you. And it's just not going to be worth it to do stuff like intergalactic travel or even interstellar travel. And that's it for today. Please provide any feedback in the comments and subscribe. And see you guys next time.